Hi everybody, Miss Panzarella here, taking a look at the example problem that looked at speed and velocity, but it was also used to look at how we calculate exact positions. So the very first question that you were given was creating a quantitative velocity versus time graph. And if I ask it to be quantitative, then you need to have the numbers. Now, your very first move should not be to create the velocity versus time graph. Because the problem that I've been seeing is that people are taking whatever the final position is. So in this case, the final position of section A was 30 and writing that the velocity is 30, and it's not. Just because you're at a position of 30 doesn't mean you're going 30 meters per second. We don't actually know the values that go on this y-axis until we calculate them. So you can never ever skip step one, and that's calculating velocity by taking the slope of the position versus time graph. Because that was our big takeaway from the big picture is the slope of the position versus time graph is velocity. So when we take the slope for section A, you get 0.75. B, we don't really have to do anything because it's just zero. It's not moving. And then for C, we end up getting negative 0.25. Now, qualitatively, this makes sense. Because when we look at it, section C is much less steep than section A. So if it's not as steep, then that means that we're not traveling as much distance and even in more time, so it has to be slower. So quantitatively, this is backing up what we thought qualitatively. Now, once we have these values, we can go ahead and plot them. So for the first 40 seconds, it was 0.75, then it was 0, and then from 80 seconds to 160, it was the negative 0.25. So that's kind of your step one and then step two. The next thing that you were asked was to rank the speed and velocity. And really the only difference with this is that speed is a scalar function and velocity is a vector, meaning that velocity cares about the direction, so whether it's positive or negative, and speed does not. So speed is just going to look at big number to small number, so it's going to be ACB, but velocity cares about the negative, so it's going to be ABC. Then you were told to solve for the average speed and average velocity over the entire time component, so that full 160 seconds. Well, distance is the total path length. So imagine that your car was driving this because something physically had to create this motion, physically created this graph. So if your car drives 30 miles away, stops and then comes 20 miles back, which is what happened in this graph, well then your odometer reading would be 50 miles higher than when you started. So that's what we would do here. We went 30 meters upwards, we didn't move, and then we went 20 meters downwards, so that total of 50 divided by 160. And again, speed does not care about the direction. It doesn't care that you went back to your reference point. It's just going to add and add and add. Whereas velocity is that displacement over time, so delta x over t, and delta x is the difference between your final position and your initial. So xf minus xi is 10 meters minus 0, because we end at the 10, we started at the reference point, and the total time is 160. So we end up getting two very different values depending on what distance measurement you're looking at. Then question number 4 was to create the mathematical model for each section. And we do need it for each section because what's happening in section A is very different than what's happening in section C. So I'm just going to go back up here to look at the models, and what you should notice right off the bat is that I don't use y equals mx plus b anymore. We've already used that to bring us to the point of xf is equal to vt plus xi. So that is your kind of standard mathematical model for Unit 2 now. But we know that we have to customize it. So in section 1, it's going to be xf is equal to the 0.75 meters per second multiplied by t. And then the initial position was just 0, so we don't put anything in for that. And now you may be wondering, well, why didn't I put in 30 meters? You know, that's the final position. Sure, that's the final position at a time of 40 seconds. But what if you had a time of 20 seconds? What would that position be? What if you had a time of 11 seconds? What would that position be? So the model is used so that no matter what numbers you're given, you could figure out the other variable. So maybe you had a position of 33.5 meters. What was the time that it took to get there? You would be able to solve for that. So in the model, we only ever put in numbers that don't change. The velocity doesn't change. The initial position doesn't change. But time and the final position, they do. So then your next one, xf is equal to vt plus xi. If your v is 0, 0 multiplied by anything is 0, so that vt goes away, leaving you with just your initial position of section B. B started at 30 meters. It didn't start at 0. We've already started and left 0. We're now at 30. And then the final is xf is equal to that negative 0.25 times t, but then your section C started at 30. So always make sure that you're kind of going along in time, following what the object actually did, because your initial position is only 0 once, and that's at the beginning. All right, so last part. The last part wants you to solve for what is the exact position at 135 seconds. And this is where the mathematical models come in. So you say, okay, well, where is 135 seconds? All right, well, it's in section C. If you just go ahead and blindly plug in 135 seconds for this model, you're going to get an answer that doesn't make any sense. You're going to get an answer that's like negative 3.75, which if you check your graph, you see that, hey, I'm not even in the negative. This doesn't make any sense. If I trace up to the graph, I can see that I'm around 15-ish, somewhere in between. So getting a negative 3.75 doesn't make any sense. So you have to say, okay, well, what could be different about this? And the fact that you're in section C tells you that your time actually started at 80 seconds. Because the mathematical model for section C doesn't care what happened in B, and it doesn't care what happened in A because something different happened. So how long are we in section C? Well, from 80 seconds to 135, it's 55 seconds. The other thing to note is that you weren't going negative 0.25 meters per second for a full 135 seconds. You did other things, but you were going negative 0.25 meters per second for 55 seconds with that initial position of 30, which now gives you an answer of 16.25, which if you check with your graph, now makes sense. So that's kind of the big thing with when you're trying to solve for an exact position, you got to make sure that your time is right. All right, hope that helped.